Holy cow, that was the wrong bumper. This was not Psychology 241. This is actually Psychology 150. How's everybody doing out there in YouTube land today? This is Dr. Roddenberry streaming to you live from my home office in Willow Springs, North Carolina. I'm representing the Rockies today. I'm a big baseball fan, and I just happen to have a Rockies shirt. Not an especially big Rockies baseball fan, but I do have the t-shirt. So my backdrop that I have today is a picture I actually took in Jekyll Island. Jekyll Island, I think that's in Georgia. If you ever get a chance, it's a really cool island with some nice beaches that you should check out. But that's my background today. I got my cup of coffee, I got my PowerPoints, and I am ready to rock and roll. How's everybody doing out there in YouTube audience? If you're listening to me right now, go ahead and check in by saying hello. Let me see you in the chat bar. Without further ado, though, I'm going to go ahead and start talking about this week's chapter as you say hello. Good morning, Salem. Is it Salem? Is it the first one, Salem? Type yes if that's right, and if not, I'll try a different pronunciation. I want to make sure that I'm getting that right on YouTube. I don't know if it's a Salem or a Selim. But at any rate, very good, Salem. Okay, very good. Thanks, just want to make sure I get that right. All right, today we're talking about Chapter 5, which is going to be a more biological chapter, just like Chapter 2 and 3 were. It's going to focus on different areas of the brain that process sensory information. It turns out that the senses and motor movements and stuff like that are a little bit easier to map and understand schematically in the nervous system than are more subtle things like facial recognition and why we think and how we're able to be logical. So sensation and perception is going to have a fairly good biological basis behind it. So we're going to spend our time talking about that today. We're going to talk a little bit about the basics of sensation and perception, what it exactly means. We're going to talk about where in the brains the sensory cortices are. They were in Chapter 2, but we're actually going to focus on where they are this particular class. And then we're going to talk a little bit about the visual pathway, how information is processed from your eyes to the back of your cerebral cortex and your occipital lobe, and then how it spreads over your temporal and parietal lobes, and how all of these processes work together to help you create complex pictures and represent things in your mind. And then we'll talk a little bit about color vision and some of the learned patterns of organization that we use to perceive and understand visual stimuli. Looks like we have another person joining the chat. If you're just joining the chat, please don't hesitate to type me a good morning in the chat bar. Look at that. It looks like Lewis is here today. Thanks for coming, Lewis. I really appreciate it. All right, sensation and perception. Actually, if you remember from Chapter 1, I suggested to you that Gustav Fechner was the first person to actually measure a mental process and demonstrated that it followed a numerically systematic relationship, that there was some sort of relationship that you could quantify that was systematic. This was Gustav Fechner. He was actually studying people's sensory perception. So you can think of sensation and perception as the first area in modern psychology, created all the way back in 1851 with the publishing of Gustav Fechner's Elements of Psychophysics. And back then, he demonstrated this thing called the just noticeable difference. Although the amount of a substance that you can perceive at any given time depends upon the context, right? Your ability to taste salt that's been diffused into a glass of water is going to differ depending upon whether or not you've just eaten a salty pizza or not. Your system's going to be sensitive to these absolute thresholds based upon context. What is not going to change, however, is the amount of that a stimulus has to change for you to perceive that change. And Gustav Fechner, was the first to identify this thing called the just noticeable difference. And it's the least amount of change in a sensory experience that can be detected half of the time. He found that a stimulus needed to change 1/40th of its original value for a human being to be able to perceive the change half the time. So you can tell the difference between a 40 and a 41-pound weight, that's 1/40th, but you can't tell the difference between 80 and an 81-pound weight if you were holding them up. In terms of wattage, you could tell the difference in brightness between a 40 and 41 watt bulb, but you could not tell the difference between an 80 and 81 watt bulb. So he was the first to demonstrate this very mathematical rule that governed our ability to sense sensory items. So his area would eventually become the modern subfield of what we call experimental psychology. Experimental psychologists study a lot of things, but one of the things that they do study is how people sense information. So if you were interested in studying hearing or sight or vision, you would want to find yourself a graduate school with a good experimental psych program. All right, so what are the 5 senses that we're going to focus on in this class? Vision, hearing, smell, taste, touch. And we're also going to talk a little bit about other senses that you don't really differentiate, but your sense of balance is another sense. Your sense of pain is different than your sense of touch. And the sense of warmth that you feel inside and on your skin is also a different sense than the sense of touch. So we're going to talk about all of these different senses over the next couple of days. Wow, looks like we have a great audience in here this morning. I see my attendance is swelled up to 9 people. Thank you very much. Good to see you, Mariah. Good to see you, Crafty Table. Good to see you, Heaven Lee, along with Salim and Lewis. Great crowd. If you're out there in the audience, don't hesitate to type hello in the chat bar. And if you want, like this broadcast and subscribe to the channel for reminders about when broadcasts are going to be had anytime you're interested. Okay, now what I want to do is I want to differentiate between sensation and perception. Okay, so your ability to consciously perceive the complexity of experiences that you perceive depends upon 2 processes. The first is what we'll call sensation, and it's the activation of sensory neurons at the level of the peripheral nervous system. The pattern of neural impulses that comes in your fingers when you feel something. The pattern of neural impulses that comes inside your eyeball when you see me on a morning broadcast. The sensation of the neurons in your ear as I talk to you and you listen to my words. Let's think of that as sensations. And those sensations, those patterns of electrical impulses are then transmitted to a part of your brain, okay, where they are then interpreted in a second process we're going to call perception. And that's the integration of these different sensory experiences so that you can recognize and discover meaningful patterns in your world. So you're looking at me and your visual cortex is giving you the representation of a face that looks like mine. However, at the same time, your auditory cortex is perceiving my voice. Those 2 things are sensed by your brain, and then they're put together so that you can perceive me, Dr. Roddenberry, right? And there are some people in the emotional center, your amygdala is even responsible for helping you decide whether or not you know the image and care about the image you're looking at. So the putting together of all these sensory experiences is what we'll call perception. And the reason that we have visual and auditory illusions is because our brain learns to interpret patterns of sensations in certain ways. And so we have habits that guide how we make quick judgments about these patterns of sensations that we see. And what happens in a visual illusion is the pattern of sensations is designed in such a way that it tricks you into coming to a false perception of what you're looking at. And we'll talk about that a little bit later in this class, okay? Now, I do want to differentiate. We talked about motor neurons and sensory neurons, and I suggested to you that motor neurons go from your central nervous system to the periphery of your body, sending actions. This is true. And sensory neurons then take information that's gathered in your body and bring it all the way back to your central nervous system. There's a third set of neurons I'd like to talk about called sensory receptor cells. And these are mostly on the periphery of your body, and their job is to change external stimulation into action potentials. Patterns of action potentials we'll call neural activity. These are called sensory receptor cells. And the process of turning light into patterns of neural activity, of changing sound waves into patterns of neural activity, that process of going from mechanical to neural, we call transduction. For better or for worse, that's just a definition. So right now your voice is transducing sound waves into meaningful patterns of neural activity that your body can then interpret. Okay, now lots of different sensory receptor types. You have mechanoreceptors, and mechanoreceptors respond to mechanical forces, right? So hearing, touch, and body position are all responsible for controlled by mechanoreceptors. So hearing, you have hair cells that are bent by sound waves that give you sound. You have receptors in your skin that respond to being displaced or pushed or stretched. All right, and then you have little fluid-filled canals in your ear that tell you which way your head happens to be leaning, because the fluid runs around and touches the hair cells that are in these little semicircular canals. You have mechanoreceptors. Then you have chemoreceptors. Smell and taste both respond to chemicals. Okay, so your taste is going to respond to chemicals in the food like salts and sugars and acids. And your nose is going to respond to odorants, which are floating molecules. So they're chemoreceptors. You have visual receptors, which we differentiate, that are located in your eyeballs. And then all over your body, you have these receptors which judge your heat relative to a desired homeostatic setting that you keep in your hypothalamus. So in a sense, you can tell when a body part gets hotter than your hypothalamus would like it to get, and you can tell when a body part is getting cooler than the hypothalamus would like it. So your hypothalamus is kind of your temperature center, and these thermoreceptors help you maintain a healthy body temperature, and they tell you when you're cold or when you're hot. And then we actually have these receptors we call nociceptors, and they're the ones that specifically transmit pain, which is different than touch. You're like, what do you mean, Chris? They both involve touch. But yes, but you have neurons that carry specifically pain information, whether or not something is sharp and acute, or whether or not something is a dull, aching pain. So we have all of these different receptor sites, and they transmit different information based upon their job. Now, if you look at the brain underneath me, you'll notice that we have the 5 primary somatosensory cortexes. I want you to know that your chemoreception, your taste, and your smell are located in your frontal lobe. Your taste and your smell are located in your frontal lobe. The 2 chemoreceptors are located in your frontal lobe. Your temporal lobe, which if you think about it on a brain, looks like where the ear should be. Think about it. Your ear has an auditory cortex on the temporal lobe. Okay? Then we have, your book actually doesn't show, it shows the primary touch cortex, and that's located in your parietal lobe, right behind your motor lobe, right? Your motor cortex. And then your occipital lobe, that's the easiest for me, is where your primary somatosensory cortex is. Your eyes are on this side, your vision center is on the back side. So my two chemorecepting sensory cortex, the gustatory and the olfactory, are in the frontal lobe. Hearing is in the temporal lobe. Touch is in the parietal lobe. Vision is in the back of the occipital lobe in the back, right? Eyes in the front, vision in the back. And so I want you to be able to know what lobes these different senses are at. Okay. Good morning, Medina. Thanks for showing up. Okay, let's see. Sensation and perception. I did talk to you. So sensory receptors are specialized cells that turn physical and chemical energy into patterns of neural activity. And so the rods and cones for vision, your hair cells for hearing, your taste receptors for taste, olfactory receptors for smell, and then these other receptor cells that you'll find in your skin and organs, right? Perception is the meaning. Okay, so you happen to know that this kind of sensory stimulation is associated with the color red. Or if you process a visual image and see the color, the shape, and you remember it in your fusiform gyrus, you might even say, hey, that's my Aunt Sandra. So that's the secondary process of perceiving. So let's talk specifically about vision today. I've got about 35 minutes and I'd like to go and talk to you a little bit about vision. What you're looking at below me is an eyeball. And there are some important structures that I want you to know about this eyeball. If you'll look at the front, you're going to see this thing called the cornea, not the cornea, but the lens and the iris. Okay, now and the pupil. Actually, I want you to look at those three things. So if you look at my eyeball right now, you will see that there is a white part, a blue part, and a black part. Okay, the black part in the very middle of your eye is actually not a black part. It is just darkness inside your eye. The black part is the hole in your eye that lets light energy in. That thing is called your pupil. It is surrounded by a colored band of muscle called the iris. Do you see my irises are kind of blue? And your irises are a muscle that can contract and get bigger, and contract and expand, allowing that pupil to become smaller or larger, thereby managing the amount of light that gets into your eye. So the thing I want you to know is the iris to pupil work together. The pupil is a hole letting light into your eye. The iris is a band of muscle that shrinks or expands to regulate the amount of light that goes in your eye. Now, it hits this thing called a lens. Think of your corrective lenses that you wear if you need glasses. Well, this lens is inside your eye, and it's clear. As you can see, this lens is clear, and what it does is it focuses light just like your glasses, your corrective lenses do, and it focuses it right on the back of your eyeball. Okay, now for some people the lens does not focus the light perfectly on the very back of the eyeball. If it's out of focus, then you may be nearsighted or farsighted. I'm farsighted, so what that means is the lens is not focusing that image perfectly on the back of my eye. It's focusing it perfectly a little bit short of the back of my eye, and that's why I am nearsighted. And so your lens focuses light energy so that it gives a perfect representation of that light energy on this structure in the back of your eyeball we'll call the retina. Okay, now the retina is actually considered part of your central nervous system. It doesn't look like a brain, but those rods and cones and the cells in that part of your eyeball actually begin the processing and interpretation of visual material. So your retina is considered part of your central nervous system. The retina contains these visual receptor cells called rods and cones. We're going to talk about them later, but they contain proteins in them that are sensitive to light stimulation. And when these proteins are stimulated by light, these proteins become active and cause the rods and cone cells to generate action potentials. So you actually have little proteins inside your rod and cone neural cells that are sensitive to light stimulation. All right. Now, when you are looking directly at something, it is focused on a part of your retina we're going to call the fovea. The fovea. Now, this fovea is so densely packed with visual receptor cells like rods and cones that you don't really even have support cells in this area. No blood cells or other support cells. So it's going to be so densely packed with these visual receptor cells. However, when you're looking directly at something, that's when you have the clearest vision, because that image is focused right on this part of your retina called the fovea, where you have the densest configuration of visual receptor cells. Now, if you look at this structure, all of this information is generated inside of your eyeball. In fact, your receptor cells respond to the information as it bounces off the back of the eyeball. So your rods and cones, if I'm looking at you, my rods and cones are actually faced backwards, and they see the light that bounces off the back of my eyeball. And then the back of those rods and cone cells all come together into this nerve that leaves your eye, and it's called the optic nerve. And this is where all of the axons of these rods and cones begin to leave the eyeball. Actually, it's a little more complex than that, but that's where the axons of the cells that connect your rods and cones leave your eyeball. And so this area contains no sensory receptors, and so you really don't see anything there. You might ask the question, Chris, why don't I have blind spots in my field of vision? Well, you have two sets of eyes, and this eye can see over here, and this eye has a different view of over here. And so you get two views of each thing you are looking at, one from your left eye and one from your right eye. And your brain fills in the missing area with the eye that doesn't have the visual image in its blind spot. I hope that makes sense. This is kind of quick, and I'm not looking at you, so it's hard to tell. All right, now here's the deal. Here are the different kinds of cells that you have in your retina. You have these two types of visual receptor cells, and these visual receptor cells called proteins called opsins that are sensitive to photons. Now you have two kinds. If you look over here, you'll notice that we're going to have rods and cone cells. Rods and cone cells. Now your rods are located mostly outside of your fovea. They're for peripheral vision. And so when I'm looking straight at something, it's falling on my fovea, and the things that are in my peripheral vision are falling on my rods and cones. Rods and cones work really well in low light, and they contain this protein called rhodopsin. Rhodopsin. Okay? Now, if you are looking at something, it is falling mostly on these visual receptor cells called cones. And these are located almost exclusively in the fovea, which is the center of the eye. They're not as sensitive to rods. They need more light stimulation in order to become activated. Okay, so the proteins inside these cells are not as sensitive to light, so they need more light photons in order to become energized. And what you're going to find is that you have three different kinds of opsins in these rods and cone cells. So some of these rods cells are sensitive to short wavelength light. Some of these cone cells are sensitive to long wavelength light, and some of these cone cells are sensitive to wavelengths of light that fall in the middle of the visual spectrum. And so what you're actually going to have are three different kinds of cone cells that are sensitive to different areas of the visible light spectrum. And this is what allows us to begin generating color vision. So your cone cells are responsible for color vision, but they need a lot of light. All right. Your rod cells are located in your peripheral vision. They're on the outside of the fovea, but they are much more sensitive to light, but they only have one type of opsin, so they cannot generate color vision. All right, now, if you look at this picture underneath me, what you're going to notice is that your rods and cone cells then run back. You see how they're facing away. The yellow, orange arrow is showing you where the light is coming in, right? And it's hitting the back wall, okay? And then those rods and cones are actually, they are focused this way. So the light's coming this way, and the rods and cones are coming this way as well. And so the light hits off the back wall of the visual of the eyeball, and it bounces into the rods and cone cells. And you see those little red and blue rods and cone cells. Now behind those, facing this way, are the axons of those rod and cone cells. And then you see how they interact with these bipolar, you can't see, or these ganglion cells, and some other cells called bipolar cells. And they connect with them. And these ganglion cells work by turning off one rod cell when another rod cell is active, turning off one cone cell when another cone cell is active. So these ganglion cells kind of work as switches, creating connections and dependencies among the rods and cone cells in your eye. So if you're seeing the color green, your green cone cell is activated, and at the same time you're seeing green, your ganglion cell is depressing the red cone so that the red cone can't see red. And that's why we never see the color reddish green. It doesn't exist. And so our ganglion cells kind of work as switches, helping our rods and cone cells work together. Now, in the middle of your vision, where you have the most cone cells, your ganglion cells almost work on a one-to-one basis with each cone cell. But in your periphery of your vision, one ganglion cell may control the work of 50 rod cells at one time. And so think of your ganglion cells as switching centers that turn some receptor neurons on and some neurons off, depending upon what is happening at a given time. All right, and so all these ganglion cells, their axons are then going to leave the eyeball through the optic nerve. And the optic nerve is basically a band of axons that is, the optic tract is going towards the back of your brain. Now here we go. So this picture right here, I want to talk a little bit more about color vision. If you look at this picture down here, what you're seeing is the visible light spectrum. So light energy comes in lots of different wavelength size. Some of it is so large that you can't see it. So X-rays are so small you can't see it. Radio waves are so big that you can't see it. So light energy comes in lots of different waves, but the human beings can only view, our visual receptor cells are sensitive to a very narrow band of light energy. We call this the visual light spectrum, the visual light spectrum. So there are radio waves out there, but you can't see them. There are X-rays out there, but you need those special Superman X-ray vision glasses to see that. So there's lots of light energy, but the only light energy that our eyeballs respond to occurs between 400 nanometers and 700 nanometers. We'll call that the visual light spectrum. So you have three different kinds of opsins in your cone cells. You have one opsin which is very sensitive to short wavelengths of light. You have another set of cone cells that are have an opsin which is sensitive to the longer wavelengths of light, and they cause the color red as opposed to blue. And then you have some of your cone cells have an opsin that is responsible and more activated by light, by wavelengths, photons of light in the middle part of the visual light spectrum. And so you're going to have these three different kinds of cone cells responding to different variations in the visual light spectrum. And that's going to give you three primary colors, the sensation of blue, the sensation of green, and the sensation of red. And then patterns of firing between these different types of cones are going to give you your secondary and your tertiary colors that you begin to perceive, like marine and teal and orange and colors like that. And so I will make a quick note. People who are colorblind, if you've ever seen somebody who is red-green colorblind or the less common yellow-blue colorblind, basically what they have is, I don't want to use the word defect, but one of their cone cells, it doesn't have the correct protein, or their protein does not respond to the photon energy in that particular part of the light spectrum. So they can't differentiate between those two colors. So if your green cones are not working, then you're going to perceive green and red. You notice how your red cones kind of go off into the green part of the distribution too. You're just going to see one color, reddish greenish, instead of reds and greens. I hope that makes sense so far. Anybody have any questions? I know I haven't asked you a lot of questions, but if you would, go ahead and type in the chat bar, say, Chris, I understand, Chris, I'm paying attention, or Chris, you lost me long ago. Go ahead and wait. Sometimes it's hard to tell. If your chemoreceptors get affected by COVID and you can no longer smell or taste for a long period of time, what does the gustatory and olfactory do when something like that happens? Wow, that's a great question. That's a great question. And the question is, what does COVID do? Does it damage you peripherally by making the sensory receptor not work? Or does it affect the area of the brain that interprets that sense, right? So it could work two ways. You could be getting the chemicals in your nose, but maybe your brain just doesn't respond to them, right? Or maybe your area of your brain is working, but that particular sense is not getting the information up there. I don't think anybody knows for sure exactly what the mechanism of COVID is right now. I would assume it has something to do with inflammation of the neurons or the neural tract, maybe that connects that sense to the part of the brain. I would argue that those senses are so ingrained and those neural pathways are so ingrained that at the time you have COVID heavenly, you can't really change that sense. You can't change the pathway of that sense. I'm not sure what happens to the brain area. That is a really great question that I couldn't answer. But that does tell me that you're paying attention to the lecture. I think that's a great, great question. Okay, Lewis and Tappy and the Crafty Table say they're doing all right. Okay, now what I want to do is I want to follow this information from the back of your eyeballs to your occipital cortex. If you look at the picture underneath me, what I want you to do is look at the picture with the eyeballs and the brain areas. And I want you to focus on the two eyeballs, and then I want you to focus on the colors red and blue over there, okay? Now, here's the deal. Each of your eyeballs is oriented a different way. So my right eyeball, the right side of my right eyeball, sees the left side of my visual world, okay? And that's the left side of that blue pair. On the other hand, yeah. No, okay, my left field of vision, my right field of vision. I take that back. It's actually, yeah, the left side of that blue field. Now, on the other hand, this eyeball, the right side of this eyeball, also sees the left visual world. So if you think about it, each eyeball sees half of your visual world on this side and half on this side. Does that make sense? So your right eyeball sees your left world and your right hemifield, your left hemifield and your right hemifield. All right, and your left eyeball sees your right hemifield and your left hemifield. Now I told you that the left side of your brain sees completely your right side of your visual world, and the right side of your brain sees completely the left side of your visual world. People who have neglect have that tumor or that stroke that causes a bleed in their right parietal lobe, and they don't see anything on the left side of their visual world, okay? So what I want you to realize is that each of your eyeballs needs to send information to the left side of your brain and the right side of your brain. And so if you'll notice, as the optic nerves leave the eyeball, there's a red and a blue, and they meet at this thing called the optic chiasm. And this is where the information from each eyeball is redirected to the correct lobe of the brain, so that you get two red messages about your left visual world on your right occipital lobe, and that you get two blue messages from different eyes on the left side, about your right hemifield on the left side of your visual cortex. All right. Now, this information all goes to your thalamus. Did you know that all of your senses, except for smell, go through your thalamus? And your thalamus is sort of a way station between your eyeballs and your brain. And what it does is it takes down an exact representation of the shadows and the movement and the location of light and dark spots on your visual field that it's going to transmit to the back of your brain, as well as color information. But it also connects your senses to one another. So if I hear snapping over here, my eyeballs know where to look to hear that snapping. So my eyeballs are tied to my ears. If I smell, let's say I'm walking down the street and I smell something really stinky, it might be dog poop on the sidewalk. My nose is going to tell me which direction to look. All of your senses are tied together, and so all of your senses travel through your thalamus on the way to the primary cortex, and this sort of allows you to connect your senses to one another. If you look here on the back part on the picture, way down in the corner, see those two little green dots? Those are the areas of your thalamus that are responsible for this sensory coordination, and this is called the superior colliculus. The superior colliculus. It's the thalamic structure that connects your vision to the other senses. And so you could have damage to this and not be able to know where to look when you heard sounds. Or maybe you wouldn't be able to locate things that you smelled in your environment with your eyes. You wouldn't know where to look to find that dog poop if there was damage to your superior colliculus. Now, if you look at the map down below, so it meets in the thalamus, that's where we get a connection, and then it travels all the way back to the primary visual cortex. And if you'll notice that, you're going to see that the primary visual cortex is in the inside part of the occipital lobe at the back of your forehead, at the back of your cerebral cortex. So if you'll see down here, you have a little blue area, and the blue on the left side of your brain represents your visual information, the visual stimulation from your right field. And if you look at the red part of the cortex on the inside of that occipital lobe on the right side, you'll notice that it corresponds with the red hemifield on the left side of your visual field. And so both of those halves of your visual cortex, of your visual field, are recorded on each half of your visual cortex, which is located at the back of your brain in the occipital lobe on the interior, the medial part of the occipital lobe. Okay? Any questions so far? Any questions? Now, here's the deal. What I'm talking about right now is what you might call perception, the perceptive process. So the information is recorded by your rods and cones in the peripheral, in your peripheral structure like the eyeball. That information is then transmitted in a set of patterns of neural impulses back to your thalamus that are then shunted off to different places. But then travels to the back of your brain, your visual cortex, where information is recorded. And we call it the primary visual cortex because it engages in what we would call primary levels of processing. That particular part of your brain, it's got, I think, 5 different areas, V1 through 5, and each one of these areas breaks down and evaluates the visual stimulus on a simple characteristic. One will evaluate the stimulus on the line on what direction it is tilted. Another part of the primary visual cortex will process which direction the image is moving. Another area will process the cone information to tell what color the stimulus is. And so the very, very, very basic visual qualities that can be abstracted from the rods and cones is processed right here in the primary visual cortex. Let's call this the process of sensation. Recording that light energy coming into our eyes on our primary visual cortex is patterns of neural activity. That's called sensation. Now, here's the deal. In order to recognize the world, we have to be able to put these sensations together. Movement, lines, shapes, colors. We have to begin to put these together and associate them together. Now, if you'll go back, I'm sorry to go all the way back, but if you'll notice right here on this picture right below me, you see we have the primary visual cortex in orange. You will notice right outside of that, closer to the middle of the brain, medial, we have a yellow area. That's going to be controlled by the visual association cortex. I mentioned association cortexes last week when I was talking about this crazy notion that we only use 10% of our brain. Much of our brain is given to association cortices, and your visual association cortex starts to put lines and shapes and movement together to create very simple objects that you begin to interpret. Does that make sense? Now, at this point, once it goes to the visual cortex and these primary qualities have been recorded, your brain then goes into what we will call perceptual mode. Your brain starts to guess what it is you are looking at. Now, what your book talks about here, with regard to this, is what we would call perceptual principles that we learn over time that allow us to make guesses about what it is we are looking at. And one of the biggest guesses that we learn to make earliest in our life is how to separate the figure from the ground. So the basic thing that you can tell right now is that I am me and I am standing in front of a background. You have realized the difference between figure and ground. If I look at this coffee cup right now, I can see the coffee cup and the wall behind it. The coffee cup is the figure and behind it is the ground. This may sound really stupid, but you actually have to learn this early in your life. In the first weeks of life, you learn to differentiate that some things are the target you're looking at and some things are behind the target that you're looking at. And that's a clue, that's sort of a visual perceptual habit that human beings will learn when early in life. Have you ever seen that? Have you ever seen that visual illusion where they ask you if you see the two faces or if you see the vase? Have you ever seen that before? What does that look like? Let's see. It's like yeah, here we go. Oh, that's horrible. That's horrible. So it's like this. Do you see the vase in the middle? The vase in the middle? Or do you see two faces? Which is the figure and which is the background? That's a very, very basic. That visual illusion challenges you because your brain has learned that faces are really important, but the thing in the middle is typically the figure. So is it the thing in the middle, the vase, or is it these two things which are very important to you, which are faces? And the figure ground illusion with the face and the vase or whatever, the vase and the two faces takes advantage of human beings' desire to separate things out into the figure and ground. I hope that makes sense. So that's sort of a basic organizational principle. We are not born with this. We have to learn this. And what these guys who would become known as the Gestalt psychologists, who actually would then become social psychologists, my forefathers, argued that human beings learn how to organize their visual world using a basic set of principles. And they named these the Gestalt principles of grouping. And these are basically learned habits of interpreting visual information. So, going left to right, proximity, similarity, continuity, closure, and illusory contours. If you look over at the first one, A, proximity, close figures are grouped as an object. So rather than say, I see 15 dots, you are more likely to say, I see 3 groups of 5 dots. If you say that I see 3 groups of 5 dots, then what you are doing is you are grouping by proximity. So if you ever walk up to a group of people, you don't count the total number of people if they're clumped into conversational groups. You'll say, wow, there appear to be 3 conversations going on. Human minds tend to group things based on proximity. If you look at the B, what you're going to notice is that you see 2 different patterns right here. You are able to see what looks like, I think, sand dunes on the left to me and straight lines that represent a calm sea on the right side. So your brain decides to break things up in your visual field based upon whether they have similar features. So it doesn't matter what this is. You notice that there are 2 different patterns in this particular visual image. So we break things based up on proximity. We break things based up on similarity. And if you look at C, now they show you the translucent pink cylinder because they want you to imagine what it looks like. But if I showed you that pink cylinder and it was solid and you saw that green thing behind it, you wouldn't say, I see a green cylinder with a pink cylinder with 2 green rectangles on it. You would say, I see a pink cylinder with a long green rectangle behind it. And so intersecting lines are interpreted as continuous. So you see the 2 lines on either side of the pink container, you automatically in your brain connect them together to make that 1 green object instead of 2 green objects. Human beings also tend to close out lines. So if we see a shape, we don't have to see that perfect shape. If we see the outline of that shape, and we see the important points. Like for a triangle, it would be the corners, or for a square, it would be the corners, or for a circle, it would be the different parts of the arc. What we can do as human beings is we close those into specific shapes. So I don't see three pink V's. Instead, I see one pink triangle in D. And then the same thing goes for E. We actually tend to create objects out of contours. Now, I promise you there is no yellow square in number E. However, each and every one of us definitely sees the yellow square in number E. And that's sort of a visual cue that we use to help organize our world. First, I said we'd start differentiating the world between what we're looking at and the things behind it, figure and ground. But over the course of your life, you begin to learn that these categories are a great way of interpreting the incomplete objects that you see. This is where perception starts. And then a quick moment, we can talk a little bit about one other form of perception we do, is that we learn how to use visual cues in the environment to tell depth, even if we if there is no depth. We sort of interpret depth in one-dimensional situations. Now over here I have this thing, binocular disparity. Because you have two eyes, and two eyes each see different, that left half of your world a little bit differently, and those two eyes see the right half of your world a little bit differently. Your brain actually interprets the difference between those images and creates what we will call true depth perception that comes with two eyes. But even in the absence of two eyes, I can still close one eye and still tell what part of my office is closer to me than the others. And that's because we use these things called monocular depth cues, which are basically learned strategies for determining relative distances. Okay, so if you see this woman's head blocks the post behind her, so I know that that girl in black, that lady in black, is in front of that street light, because I can see all of her, but I can't see all of that street light. If you want to ask me who is closer to me, I can tell you that that fellow in the Redskins shirt, the 83 shirt, is a little bit higher in the visual field than that fellow with the white shirt and the tie over at the far right. So I'm going to make the guess that the fellow in the red shirt is farther away from me. Relative size. If you look at the guy in the white shirt, he is with the tie on the right side, he is way bigger than that fellow standing back at the crosswalk with the briefcase in the white shirt. See how he is 3 times as tall as that guy. However, I know that based on relative size and familiar size, that those two guys should be similar in their size. And the fact that one guy is so much smaller, I interpret him as being really, really far away. Linear perspective. If you'll see, it's not as sharp here, but you'll notice that crosswalk is supposed to be going parallel, but it looks like as it goes from bottom to top, it's actually going together. We call that linear perspective. And if you look at the lines on the crosswalk, as we get farther away, they start getting closer and closer together. This linear perspective and the texture gradient also are used by us to guesstimate difference. So check it out. Look at this. I'm going to draw you a picture. Which mountain is in front, A or B, right? Okay. And then what I'm going to do is I'm going to put a road heading into that mountain. So right there, this is a parallel road. But see how it gets closer together? You can tell that it's going off in the distance. And then here are the lines that are in the middle of the road, right? And as we go farther away, they get closer together. And here's my friend Rex. He's standing right here. And you'll see that my friend Ted is way back here. Ted is much smaller and Ted is higher in the visual field. So we have the linear gradient. 1, we have the texture pattern. 2, we have height in the field. 3, we have relative size. 4, and we have interposition. 5. All of these cues allow me to guess what the height, which is farther or closer in the picture. Okay. I'm sorry I ran over today. I'm 9:54. We're going to talk about the other senses on tomorrow, and tonight in class we will be talking about people with bizarre perceptual disorders, and hopefully you will find that interesting. So I do hope to see you tonight in webinar at 7 p.m. If you don't have any questions, I'm going to go ahead and say goodbye for today. Have a great day, and I will see you tonight in webinar or tomorrow morning. Take care.